Our next speaker, Woody Rickerson, will be explaining how I can keep my Tesla charged with the grid. Woody Rickerson became ERCOT's Vice President of Grid Planning and Operations in October 2015. In his role, he oversees planning activities and electric grid operations. Mr. Rickerson brings more than 25 years of electric industry experience, including 15 years at ERCOT, to this role. Most recently, he has served as Director of Grid Coordination, overseeing 7 departments, including outage coordination, model administration, model maintenance, resource integration, engineering development, operations training, and advanced network applications. He also was involved in developing tools to operate the ERCOT grid, beginning with the development of ERCOT zonal market system in 2000, and has served in a number of increasingly responsible roles prior to his current role. A licensed professional engineer, Mr. Rickerson has worked for utilities in Texas, Arizona, and New Mexico. He has a bachelor's degree in electrical engineering from New Mexico State and a master's degree in engineering management from the University of Colorado. He also completed the Cockrell School of Engineering Leadership Certificate Program. Thank you.
All right, well, thank you. It's an honor to be able to come and speak to you today. I'm always very excited to get to talk about the power industry. It's a very exciting time, and there are a lot of things changing. I have 2 sons that are mechanical engineers at A&M, and they kind of roll their eyes when I say there's something exciting going on in the electric industry. So Dr. Shea, I don't know where Dr. Shea is, but I failed on the first 2, but I've got 1 more at home, and I'm hoping he will be my electrical engineer. So anyway, let's go ahead and go forward here. So first of all, I wanted to give you a little insight into ERCOT. ERCOT is an acronym, the Electric Reliability Council of Texas. In 1999, the Texas legislature restructured the Texas electric market. And it did so with the idea of 4 main purposes: system reliability, competitive wholesale market, open access to transmission, and facilitating a competitive retail market. So when you think about the power grid across the country, across North America, there really are 3. So what we see here is an eastern interconnect, a western interconnect, and then you see ERCOT. So these grids are separate. ERCOT could be up and running, and the rest of the other 2 grids could actually be in a blackout condition, and ERCOT would be unaffected, and likewise with the other ones. So as grids grew from the coast, they kind of met in the middle, and they weren't synchronous. And those boundaries still exist today. In terms of size, the Western Interconnect is about 140 gigawatts at peak. ERCOT's about 71, and the Eastern Interconnect is about 610. So that 71 gigawatts is kind of a point of reference as we go through the rest of this presentation. So keep that 71 gigawatts of power in mind. That is the peak amount of power that's been used in the ERCOT grid. That occurred last summer. So the map there represents, is one of our tools that we use, but that is the ERCOT grid. The different colors represent different voltage levels. The green is our 345,000 volt transmission line. Those are the big ones. That's really the backbone of the system. 46,000 miles of transmission, 514 thermal generation units, 11,000 wind turbines. Has anyone driven through West Texas lately and seen all the wind turbines, especially at night where you see all the lights? 50,000 switching devices and 4,300 substations, and 1,000 telemetry signals coming into our control room. over 100,000 telemetry signals coming into our control room. And we also manage hundreds of thousands of coordinated equipment outages each year to keep the system up and running. So that system reliability is the main focus of what I work on. So current records, so this is just to kind of give you some background. Current records as of December 2016. So like I said, our peak demand, 71 gigawatts. Our winter peak is 57, so we're a summer peaking grid. Wind generation records, 16,000 megawatts. So that's 16,000 megawatts of wind generation that were occurring on December 25th, Christmas Day this year. And we have those divided up into regions. Most of that is non-coastal. So we have a section in the Corpus area, and we have what we call West Texas and the Panhandle wind. That's the number I want you to focus on, though. 47% of the load served by wind generation. So that means that every light bulb, every air conditioner, think about all the electric load in the ERCOT grid. And the ERCOT grid represents about 85% of the Texas load. There are some parts of Texas that are outside of the ERCOT grid. But 47% of that load was supplied by generation that comes from an intermittent resource. As an engineer, that's a challenge, and it's a little unnerving sometimes. Our active wind capacity at the time we put this together was about 18,000 megawatts. So on that particular day, 16,000 megawatts was running. So that's a lot of wind blowing in a lot of places. It's really a pretty amazing amount of wind. I put this in just to show you that this is the load in ERCOT builds throughout the summer. And as this load builds from June to July to August to September, the wind production falls off. So the wind, not only seasonally does it not blow in exactly the right time, in a daily basis, it tends to not blow over peak as well. That's one of the drawbacks. But change is coming. So this is what I want to focus on today. So if we look back at 2013, and this is very similar to some of the slides you've just seen, 2013 energy generation, this is the energy that was generated, electric energy that was generated by fuel type for all of 2013. And we see 41% coming from natural gas, 37% from coal, 12% from nuclear, 10% from wind, and then we have a slice there that's other. If we look at 2016, we see a pretty dramatic change. We see our natural gas production going up, but we see a big drop in coal. The amount of energy generated from coal has dropped considerably, and the amount of energy coming from wind has also gone up. Now, if I were to go back and look at 2010 and compare 2010 to 2013, you would not see that change. This is a dramatic change, and I think it's going to continue, and you're going to see this escalate even more. So this is a chart. If you start at the top, is the year 2000. We had 116 megawatts of wind. And if you look at the bottom, this is 2019, and it's projected to be more than 28,000 megawatts of wind. Today, we are at right at that 18,000 mark, 2016. And so you see a dramatic increase in wind. What's expected to be built, people that are developing wind plants, people that have made financial investments, that there's a dramatic increase is on the way. Equally dramatic is solar generation. So this chart, and if you look, this peaks out at 2,500 megawatts at the bottom, where our previous chart was 25,000. 2010, 15 megawatts. 2020, 2,573 megawatts. And this continues to be one of the places we expect to see the most growth in new generation. It's a dramatic shift. So ERCOT's primary challenge for maintaining reliability will be adapting to the changing portfolio of generation technology. For years and years, we had thermally dispatched units. That's going to change. And adapting to that changing resource mix is the thing that keeps most of our engineers busy, developing tools, developing forecasts, developing a market. All those things are key in maintaining that reliability. Frequency control. We have to maintain the ERCOT grid at 60 hertz. If it goes too fast or if it goes too slow, we have blackouts. Frequency control is one of the major challenges. We'll talk about that. System inertia is a aspect of the grid that most people aren't familiar with, and we'll talk about that. And finally, the location of these new resources. There are places where it's better, you get more bang for your buck as a developer of renewables than you do in other places. So let's talk about frequency control first. So the key thing here is that generation has to equal load at all times. So if I were to go to the back of the room and turn the lights off, somewhere a generator would produce less power, matching the change in load. So as cities and towns and industries increase or decrease production, generators chase that and maintain that balance. And that's a major aspect of operating the grid. To maintain that 60 hertz, you have to have generation following load. So the blue line here, there's two charts. This is just to demonstrate what I'm talking about. On the left-hand side, you see frequency, and that corresponds with the red line, and you see megawatts on the other. So this is a generator that's generating megawatts, and at about 11:17, we see a drop in frequency. That drop in frequency is because a generator tripped offline. So the generator that's still online increases production to make up for what was lost. And you can think of this as the cruise control in your car. When you come up to a hill, the cruise control automatically gives the car more gas and you maintain the speed that you had. That's what we expect, and that's the way the grid has operated for as long as there's been a grid. But what happens when you have wind turbines? They can't increase the wind, and they don't have anything in reserve. So that's part of the problem that we have to deal with. So this is a wind farm response following a unit generator trip. So once again, you got frequency on your left, and you have megawatts on the right. And we see a drop in frequency, and in this case, the wind resource had some turbines that weren't turning, and so they were able to turn those turbines on and respond to the frequency and help maintain it. But even then, you'll see that while that frequency is below 60 hertz, we don't get a good uniform response like we do from a thermal unit. If you remember the thermal unit, nice, even output. The wind units aren't capable of doing that. And then, if you look at this next chart, wind response to high frequency. So if high frequency occurs because some load suddenly turned off, we want our generation to come down. Well, in this case, the wind turbines can take turbines offline and respond. So they're good at responding on the low end, but not so good at responding to low frequency. And in fact, if you look at the chart on the right-hand side, you'll see one of the problems. The wind turbines the wind unit has taken some turbines offline. The frequency goes high again, and the wind farm's unable to respond. So it's just not as good as the thermal unit for maintaining that frequency. Another thing that we have to do to make up for that is what we call ancillary service requirements. So ancillary service is backup generation that we buy to help maintain frequency. And there's a market that people bid into that have generators in order to sell their ancillary services. And the chart you see here has January to December on the left and hours of the day going across the bottom. The colors represent the amount of responsive reserve service we have to buy. Now, if you looked at this chart 15 years ago, the entire chart would have been blue. We would have bought 2,300 megawatts all the time. So what happens when you have 47% of your generation coming from wind? The chart changes. And you'll see we're buying in hours and parts of the month where we have a higher penetration of wind, we have to buy more ancillary services. So that cheap wind power that everyone likes has to be supplemented with backup thermal generation that can respond to the variations in load. The next chart is similar. This is another ancillary service that we buy called non-spin reserve service. And it's procured based on the risk of net load, which is we have times of the day when load is increasing and wind is going down at the same time. And so the net effect is a much more dramatic ramp of load. And so we buy non-spin to make up for those times, to make sure we have enough generation in the back to cover the load during those times and maintain that frequency. So when we think about wind and we think about the benefits of wind and renewable resources, you need to factor these things in as well. These are the tools that you need in order to make the wind work. And this is a real cost that comes through everyone's bill when you pay your electric bill. It's a cost to industry, and it's a cost to anyone that uses electricity. In order to maintain that reliable grid, the cost of ancillary services go up. System inertia. So system inertia is the amount of spinning mass the system has. So we have synchronous generators that are spinning at 60 hertz. And when a generator trips off, there's a certain amount of inertia that is maintained through the system depending on how many units you have online. Unfortunately, renewable units don't have any inertia. Because of their power is supplied through inverters, those big blades don't supply any inertia for the grid. And what you have here, ignore the green line for now, this is the level of inertia measured in megawatt seconds that was for April, which is our lowest period for inertia. And you see different layers there. The bottom layer is inertia that was supplied by nuclear units. The second layer is by coal. The third layer is simple cycle, mostly gas. And the third layer there is combined cycle plants. And so you see, that's the inertia that's supplied. Now the critical number here is the red line at about 100,000 megawatt seconds. If we drop below that level, we have to go procure thermal generation in order to maintain enough inertia to be reliable. So currently, we haven't had to buy thermal generation to maintain inertia, but in the near future, we will have to. It will become another ancillary service product that we have to purchase. So we monitor it today. We have alarms that go off if it gets too low. But you can see on April 10th, that was our lowest point for the year. And we were still 13 or 14,000 megawatt seconds at that point, so we were okay. But as we incorporate more and more renewables, that number is going to continue to go down, and that will be another expense of incorporating more and more renewables. So something to think about and consider. This is the average inertia constant per type of generation. So you see combustion turbines are our best, 5.29. And you'll see at the far right-hand side, you'll see wind and solar PV. So they don't contribute to our inertia at all, our system inertia. And you see different levels for different other units there. Location of new resources. So in 2010, a bill was passed to complete the competitive renewable energy zones. This consisted of a series of areas where wind generation was very good. And it was completed in 2013 at a cost of about $7 billion. And if you look at the map on the right, the red lines represent that 345 kV network that we talked about earlier. That's kind of the backbone of the system. And the yellow lines are 345,000 kV additions to that existing grid. So between 2010 and 2013, all those yellow lines were built. And the reason they were built was because those two places where I've put wind, those were very rich wind zones. Lots of wind blows there, and it's a great place to build wind farms. But there's no way to get the wind farms from out here where the wind is good to Dallas and Houston and Austin, San Antonio. Without this infrastructure, that wind would never be delivered to where the load is. So at the cost of $7 billion, we now have an infrastructure in place so that wind farms can be built in the Panhandle and in West Texas, and that power can be delivered. Now, the best solar resource areas are in far West Texas, where there's currently a limited transmission. So if you look at solar, that's the best. If you look at solar maps where the best solar farms are going to be built, that's where developers are going to want to build solar plants. And you see there's no infrastructure in that area. There are some lower level transmission lines, but there's not the big 345 kV infrastructure there to be able to deliver that 2,500 megawatts of solar we looked at earlier to Dallas and Houston, San Antonio, or Austin and San Antonio. So and the reason I show this map is because the location of solar and wind resources are a long ways from load. And to get the power, because you can't save the power, we don't have batteries on the level of transmission. The only way to get the power from the good locations to where people have built load is through transmission lines.
How far west is that?
Well, if you look at that's about El Paso right there, where I have the red dot. So we're talking about Odessa, Midland right here. And that solar area, this is New Mexico. If you think south of New Mexico, right where the flat part is there, that area out there is a really good solar area. I mean, and solar plants can be built in other areas. You know, Austin and San Antonio, other places there've been solar plants built near there. But if you're a developer and you want to get the most power for your dollar of investment, you're going to build in places where the solar return is the greatest. And unfortunately, those places are far from load. So that's those are the three things that frequency. It's hard to make the wind blow harder when you need more power. Kind of hard to make that happen. So you got to hold something in reserve, and you got to pay for that. And you got to pay people to hold stuff in reserve. So frequency is one challenge. What was my second one? Inertia because solar and wind are inverter based. They can't contribute to inertia, and there's a certain level of inertia with today's technology that we have to have. Now, that could change in the future, but right now that's a major challenge. That's something we have to monitor, and that's something we may have to spend money on to maintain. And lastly, the location. Houston is not in West Texas. If Houston was in West Texas, then you would have a lot smaller problem. So last slide here. If you're interested in more, this is a link. This is our long-term system assessment. In that long-term system assessment, we talk about what the future holds. And we have several scenarios here that we've looked at. Scenarios such as a Texas recession. What would happen? What's going to happen in the next 5 years if we had a major recession? What would happen if natural gas prices remain low? What would happen if high efficiency and large levels of distributed generation were manifested in the next 6 years? And so these are all things that we think could happen, possible scenarios. Some of them, like the environmental mandate there, has no coal. What would take the place of it? How would we do that? The thing that's unique to all of these scenarios, though, is the solar. We don't have solar today, but in 6 years, in all the scenarios, we expect there to be a large amount of solar serving power in Texas. So if you have more questions about that, that is available publicly on the ERCOT website, and that link will get you there. And that's all I have this morning. Any questions? Yes, sir.
Could you talk a little bit about the effects of net metering?
Of net metering?
Net metering from solar on rooftops?
Sure. So ERCOT bases its load forecast on metering. And so we look at what happened the previous year based on meter data, and we anticipate where the load's going to go the next year. If you as a consumer go out and install solar panel behind the same meter that your load is monitored behind, then your load will be less next year and our estimates will be off, our forecasts will be off. So net metering is a real problem for us from a forecasting standpoint. And forecasts are key when we're talking about resource adequacy and having enough generation online for the next day.
One of the ways to counteract the inertia of the grid is to have energy storage, especially large energy storage like pumped hydroelectric and compressed air. Do we have any such projects in ERCOT?
We're very short on water resources capable of storing, but you're right. Storage would be an answer. We have 6 or 7 very, very small hydro units, and that is not really a viable option. There are people exploring and looking at compressed air storage, but the economics of that have not proven to be something that has made it implemented on a wide basis. Yes, sir.
The first gentleman asked my first question, which was about the home energy generation, but the second one was, what is weird about Austin Energy, and why are they not, why are those of us who live in Austin unable to buy power from competitive power generation sources?
Why are you not able to?
We're not able to, that's correct. You can only buy power from
Right.
Austin.
As part of that Senate Bill 7, many municipals basically opted out of competition, and they act as one customer. So they go out as one large customer and buy on behalf of their region. Austin Energy isn't alone in that. There are several municipals that do that.
Could I ask a question? Yeah, so back to the solar. I have the impression that there are some parts of the country, it might be Oregon and Washington State, for example, and California, West Coast, where homeowner solar really is distributed and interacting with the grid in an effective way. So first question is, would you agree with that? And then if you would, why don't we see more of that in Texas?
I think the answer to that question is, and California in particular has had a lot of problems with it. the key to integrating rooftop solar in the big grid that I've shown is awareness of where it is. That's, if we can see it, and if we can model it and forecast it, then we can manage it. But that's a big step right now. Getting to the point where individual rooftop solar stuff is aggregated to the level where we can see it on the ERCOT grid is a major step, and there's a lot of cost associated with that. I think we're going there, but it may take some time to get there. So right now, our first step is to, on a distribution level, which is the lower KV level, is to map the largest units. And these are units that are like 1 megawatt and larger. And they represent roughly 1% of our load right now. There's about 700 megawatts of that. So that's our first step. So I think we're going there, but I think it'll take a while to get there. And it's due to cost.
So I have a two-part question. The first question is, what is the maximum amount of wind power that is suitable, to produce within ERCOT, given the fact that you need a minimal inertia in the system, right? I mean, you cannot go to 100% wind, right? Because your requirement of minimal inertia. And then the second question that I want to ask is, given the fact that you have to supply the decrease in power for wind for whatever reason with thermal, and given that when you're ramping up thermal and ramping down, these transients generate inefficiencies in the power cycle. So how do you actually consider that going to more and more wind would affect the outcome in terms of CO2 emissions, for example?
Okay, so as far as your first question goes, it really, if you think of the generation that's online in two, renewable and then thermal, how far we can let that percentage go really depends on what's in that. If it was all combustion turbines, it could go a lot higher. If it were simple cycle, not so much. We'll go over 50% this year, more than likely. And I think the upper limit is somewhere beyond that, but it's hard to answer that question until you know what the rest of the generation is that's online and what's running. And your second question, as far as thermal units that are used in ramping, and currently the dispatch is, it's market-based.
Okay.
So our ancillary services, the things we choose, are based on bids from people who own those power plants. So it's completely bid-based. Okay? Is that it? I'm getting the hook. Thank you guys very much. I appreciate being able to come and talk to you.
Thank you.
Yep.
Great time.